been doing over the last few years with Thibaut Damour, Marc Hainaut, Axel Kleinschmidt from my institute, and Christoph Meissner from Warsaw University. And this work has been done in various combinations. So it's not a single paper I want to talk about, but more about this whole line of research. So I thought I would start with a wish list, because this is the kind of list we always put up many, many years ago when I was still working on supergravity. We always started out with this kind of list of things, questions we would like to answer. And importantly, we haven't been able to answer any of these questions, even after more than 30 years. And it even seems that these questions have faded a little bit away, even in string theory also, because if I remember, I was at the string conference last year in Okinawa. Actually, there was very little mention of any of this, except for perhaps for this swampland idea. Now, as I said, we put this up many years ago, but there's one thing that has changed since then, which is that now the experimental results from LHC are out, as you know very well. And as you can see, you don't have to look at this in detail, because this is something you can download from the Atlas or CMS homepages. And what you see here is basically nothing but exclusion limits. So many, 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 many ideas that have been popular over the past 30 years are now more or less off the table. In particular, the idea of low energy supersymmetry now seems to be almost dead. I mean, there's still people who follow this line of thought, but it's become now very implausible that this is the way that nature really takes. And in particular, one conclusion you can draw from these results is not only that there are no hints whatsoever of new physics, but the fact that the standard model, as is, can very well or could very well survive all the way up to the Planck scale. So no SUSY particles, no large extra dimensions, no nothing. And one argument for this is if you look at the couplings that have been now measured, in particular top quark mass and such things, it turns out that if you look at all the couplings and evolve them according to the renormalization group, to the Planck scale, then nothing dramatic happens. So in particular, the Higgs mass is in a place where it's such that you can evolve all the couplings to the Planck scale. There's no Landau pole up to that point. There's a little bit of an issue with instability, but that can be rectified by sort of mild modifications of the standard model. Well, naturalness remains an issue, that's true, but it seems like nature does not make use of low energy supersymmetry to answer that question. So it has to be something else.
But is that the only conceptual issue that survives taking standard model all the way up to Planck scale?
Yes, in some sense, everything's consistent, but you might, of course, there's still the problem, what keeps these mass values, what keeps the electroweak scale so small in comparison to the Planck scale. That problem is still there. Okay, so
the beta function of the self-coupling of the Higgs is now known to be negative.
Well, that's this issue about the instability. Yes, it goes underwater around 10 to the 11 GeV, but by a very small amount. I mean, this is now confirmed with the existing values of top quark masses and Higgs masses that it does go underwater for a little bit. But for example, we have been working on some model with an extra Higgs scalar around also around 1 TeV or below. And with this kind of very weakly coupled extra object, you can actually push the couplings above. So that is just what I'm saying here. It doesn't take much to cure this. It does not take a radical modification of the standard model. And I think there are even people who don't take this very seriously. Anyway, so the conclusion is, to repeat, so far at least the standard model could survive more or less as is all the way to the Planck scale. So now what's the view of string theory on this? And actually, I'm really curious what people here think about this. Well, it's been known for a very long time that, there's a very large number of string vacua. This actually was realized already more than 30 years ago by Strelekens and co-workers. And he has a recent reprint from 2016 where he sort of elaborates this a little bit. And there was this famous number 10 to the 500. But this has now more recently gone up to 10 to the 272,000. And in particular, in these compactification gauge groups that you will get look like this. This is very far from the standard model. And I remember the Kokinawa string conference, I was sitting with these people, Marty Taylor at the table, and said, how do you want to ever get the standard model out of this? You know, already one E8 is a very large group for this. And then someone said, yes, you know, from the first formulation of the atomic hypothesis by Democritus until its confirmation, it took like 2,000 or 3,000 years. So that's now the scale we should think about. There's also this raging debate in the string community about the issue of the cosmological constant. Again, something where I'm very curious to hear what the opinions are about this here in this institute. Yes, that's really pity. I know he's not, he doesn't agree with this. But anyway, you know, all of this somehow goes in precisely the opposite direction from what's suggested by these results of LHC. And it seems to me, for string theory, the conventional ways of trying to make contact with the real world, if they have to rely on this, I don't find this very appealing. But maybe there's some other way completely different way to link the theory to the real world. In particular, there's the question, if it's really true that it's just the standard model, how does this fit here? Because many of these compactifications are predicated on the assumption of low energy supersymmetry. There was even this article, there's this German weekly magazine, Der Spiegel, and it had a title story even entitled, do we live in a universe that just cannot exist? And you can link to this article. If you go to Kumrun Wafa's homepage, there's a link to this article in German. So, so that's the state of the art in string theory at the moment, as it looks.
Gauge groups of this kind, these are consistent with lambda equal to 0, is it right?
Oh, this I don't know because no, I don't want to make any statement about this because I just looked through the paper and looked for a representative gauge group they get out of this, and this was one of the examples I found. Anyway, it doesn't really matter whether we have 38 E8s or 27. Who cares? It's far too big anyway. Okay, so what I want to do in this talk, I want to give you a completely different view on this and how to get the standard model, or at least, well, the kinematical side of it. So there are very few people working in this direction, therefore we're far from a finalized proposal. And this proposal makes use of several ingredients, which I'm going to explain a little, but there's not that much time, so you can ask me questions, and I'm still here until this evening, late this evening, so we can discuss. So first of all, there's something called BKL. Secondly, there's something called E10. And thirdly, this whole discussion brings back n equals 8 supergravity, but in a sort of from a very different perspective. So so here the main concern is really, we have all these beautiful theories, or we think they're beautiful, but at the end of the day, the question is really, how does this really relate to the real world? Okay. So I'm not going through these items, and you can at any point just interrupt me and ask questions. Now, first part of the story is what's called the BKL analysis of space-like singularities, because this is where we see the emergence of these huge symmetries. So this goes back to Belinsky, Khalatnikov, and Lifshitz. That's what BKL stands for. It's so old you can even read about it in Landau-Lifshitz Volume 2 at the end. In fact, 3 weeks ago I was at the Landau Institute for Isaac Khalatnikov's 100th birthday. He was sitting there, but amazing. So what's this? So what you see here is a cosmological spacetime with a Big Bang singularity, Big Bang hypersurface. It's space-like, and this is the same, means the same, like saying that you have causal decoupling of the points. I'm sure you've seen this picture in connection with. Good morning, Shiraz. Welcome to this seminar. So what you see here is a cosmological space-time, which, as I said, I'm sure you've seen in connection with inflationary cosmology, because this is just what they call the horizon problem. But BKL was much before inflationary cosmology. Anyway, what you see here is these light cones that become smaller and smaller. And as you approach the initial hypersurface, these points become spatially decoupled, causally decoupled. This fact was invoked by Belinsky-Khalatnikov in their analysis of cosmological singularities to argue that as you approach the singularity, the causal decoupling of spatial points implies that spatial gradients become much smaller in comparison with time derivatives. They may still blow up, but they blow up in such a way that time derivatives overwhelm everything else as you approach this hypersurface. So another way to say this is that what happens here is a kind of effective dimensional reduction to one time dimension as you approach the initial hypersurface. And their idea was to get a better understanding of these singularities by performing a kind of spatial expansion in spatial gradients, which are small, as I said, in comparison with time derivatives. So what you start out with is a sort of Kasner solution, but where the Kasner coefficients depend on the space point where you are. And then you set up an expansion and try to ensure that it converges. Well, one surprise that they found this doesn't always converge. In fact, in four-dimensional gravity, it does not converge. But what happens is that there sort of starts a chaotic behavior in the sense that these Kasner coefficients oscillate wildly as you approach the initial hypersurface. And this is what has been referred to as chaotic oscillations of the metric as you approach the singularity. In other words, this is also the behavior that you would experience when you fall into a black hole, get squashed by the singularity. It's not that you just get uniformly squashed, but you get you fall into a kind of mixer that in the sense you get stretched and squashed an infinite number of times between time epsilon and time 0. So that, I think, to me, is one of the most important results in mathematical cosmology of the last 50 years. It has really not been rewarded appropriately, but anyway.
Sorry, I didn't quite get why there's an asymmetry between the time gradient and the space.
That's a hypothesis. It's a hypothesis.
That's a hypothesis.
It's a hypothesis. You see, this BKL hypothesis, in the strict sense of the word, has not been proven. It has been proven for some cases where actually these chaotic oscillations are absent, and then you can prove convergence of these expansions and so on, but not in the general case. The interesting case is when you have these chaotic oscillations. So I said there's a one-dimensional induction, and in a more general context, you can also view cosmological evolution as a one-dimensional motion, but not in space-time or anything, but in abstract space, namely the moduli space of three geometries. This is sort of Wheeler-DeWitt point of view. So the spatial moduli space, the space of d geometries, or called superspace by Wheeler, nothing to do with Fermions, looks like this. So you have the space of spatial metrics and divided by spatial diffeomorphisms. So you can view cosmological evolution at so you choose a cosmic time coordinate, and then at each point in time you have a certain spatial geometry, and the dynamics of all this is described by Einstein's equations. And furthermore, if you perform a canonical quantization of this, you're led to the so-called Wheeler-DeWitt equation. This was already done 50 years ago. And the wave function is really a wave functional that lives on this rather abstract space. It's also sometimes called wave function of the universe. Now, the point of view here is, of course, that if one aims for unification of space-time, matter, and gravitation, this moduli space should also incorporate matter degrees of freedom, but not simply as a direct product of gravity times matter, but we want to unify. And therefore the question is, can one, quote unquote, simplify this moduli space by means of embedding it or describing it in terms of some abstract coset space G divided by K of G. And this is inspired by supergravity, because in supergravity higher dimensionals, supergravity scalar sectors or moduli spaces are usually just given by some non-compact group divided by its maximal compact subgroup. So famous example is n equals 8 supergravity, where G is equal to E is 7, and the compact subgroup is SU8. So the main conjecture here will be G, that G is equal to E10, and K of G is the K of E10, which is the compact subgroup, which I'll get to in a moment. Of course, I have to tell you what this is.
This is the main conjecture for what? This is a moduli space of what?
Well, this is the moduli space of M theory. I hate to use these grandiose words, but just for you to imagine what we're after. And you know, this one-dimensional also fits with a conjecture that was made by Bernard Juliat, actually. Just looking at this table of the groups that arise in dimensional reduction, he was led to E10. I mean, it's really like E7, E8, E9, E10. It's not more than that. We will see.
So sorry, and is this conjecture of a classical evolution of the equations of M theory or something else?
Yeah, in first approximation, yes.
So this is a conjecture we could just check, right? I mean, you could
Up to a certain extent. You will see how far it has been checked. So
this also includes the superspace of Wheeler? No.
yes, in some sense, this is supposed to replace the Wheeler superspace, because the abstract space of three geometries is much more difficult. A group, if it can be given, endowed with a group theoretical structure in some way.
How do you identify a finite dimensional slice in the infinite dimensional space?
No, I mean the finite dimensional, I mean each point in this moduli space is a three-dimensional geometry. That's the, and this.
And this is finite dimensional space.
What the, well, the point, it's a three-dimensional geometry associated with a finite dimensional, three-dimensional hypersurface. Yes.
No, sorry, I didn't understand. So if you think of the space of matrix modular diffeomorphisms,
Yes.
that space is infinite dimensional.
Yes, exactly.
Now that is to be replaced by
That is to be replaced by
E10
this,
divided by
yeah,
K.
in a sense that I will try to make more precise.
Which is finite dimensional.
E10 over K10 is not finite dimensional, quite the contrary. You will see. Anyway, let's have a look at the Wheeler-DeWitt.
Just one quick. This includes the Fermions as well. Or just
No, for the moment, I'm just talking about the bosons. Second part of my talk will be devoted to fermions. So for the moment, it's just bosons.
By bosons, do you also include the three form?
Yes, you will see. You will see. You will all see all this. Okay, so here's the Wheeler-DeWitt Hamiltonian, kinetic part, potential part, there may be other parts from matter degrees of freedom with the DeWitt metric. And in this BKL spirit, I will now, because this is a constraint equation, holds at each spatial point, so it's really continuous infinity of equations. So let's go to one spatial point, and then this thing simplifies very much. In particular, we also take the spatial metric to be diagonal, as like in BKL, but with direction-dependent scale factors. So this is not isotropic, but in first approximation, it's homogeneous. And then you can, out of this, extract an effective Hamiltonian. So this is just the pi's, the momenta associated to these scale factors. And this actually is just a free particle, free relativistic particle. Why is that? Well, one of the famous things about the DeWitt Hamiltonian is the indefiniteness of this kinetic term. This is due to the conformal scaling with conformal factor. So it comes out to have precisely, in this reduction, Lorentzian signature, minus, plus, plus, plus. And if you take this thing by itself, it's just a relativistic free particle.
Still for the spatial.
We're just talking about the spatial metric, yes. And the relativistic particle does not move in real space, but in this abstract space spanned by or coordinatized by these scale factors. Now, the effective potential you get out of all this rest. Now, when you do this analysis, of course, it's extremely complicated. And you would like to sort of integrate out these degrees of freedom. Of course, it's, as I said, it's extremely complicated, but the BKL limit leads to a dramatic simplification. Because what comes out of this analysis, and this you can read out in the review I wrote some years ago with Damour and Hainaut, that it's a sort of superposition of Toda-like exponential potentials. And it's a very complicated superposition of such potentials, but as you approach the singularity, these exponentials become sharper and sharper and steeper. And as you reach the singularity, they become like infinite walls. And in this limit, you have infinite walls, then all the walls behind are screened by the walls that are next to you. And then it is in this approximation that you get this extreme simplification. And then you get a theory that has this kinetic term and the potential that's just like walls. So it's like a free relativistic particle that just bounces around and by reflecting on these walls. And this just gives what in BKL language would be the chaotic oscillations.
Quick question, if it doesn't take too long. I understand that because you're going to the singularity, spatial derivatives are less important, and so it becomes effectively time derivative,
yes.
Point by point. But I didn't understand the motivation for restricting to diagonal metrics.
No, this is an approximation, and the off-diagonal metrics, the off-diagonal components are then somehow incorporated into this. There are certain walls.
But somehow the off-diagonal degrees of freedom are heavier than the diagonal degrees of freedom.
No, you shouldn't think about heavy. Just think about these will perturb this Hamiltonian. They will introduce an effective correction to the potential. And there are certain walls are associated with these off-diagonal degrees of freedom.
I'll ask you later, but I would have thought the natural thing would have been to write on a Hamiltonian system with its degrees of freedom being the full metric modular. Why do you do this?
Yeah.
Well, you will see in a moment, because that's important for the group theory. Okay? So we first of all remain diagonal, and then you have these simplifications, and furthermore these wall forms. These theta functions, infinite step functions, so it's 0 on one side, and so it looks like this. So it's like this, and then it's like this. So just the particle bounces off. So there are linear forms in this beta space, which have this particular, you can write them like this. where this is of course the linear dependence in beta, so that's the beta coordinates. Then here's the width metric, or what remains of it in this reduction. And then you have certain wall coefficients, or coefficients of this that characterize these linear forms over which you sum here.
The Gell-Mann is a numerical matrix or is a function of beta? It's not
No, it's not. It's simply numerical metrics. It's simply numerical. It's simply a numerical matrix.
Is pi m something canonical conjugates to the beta m?
Yes, exactly. Okay, now this is important. Now you can see why I wanted to start out with diagonal, because this is, in some sense, this is one of the more important slides in my talk. Because this gives you the relation between the abstract group theory and the Einstein, the theory, the degrees of freedom of the metric or gravitational theory. Now, first of all, you identify the space of diagonal degrees of freedom with the Cartan subalgebra of a certain Lie algebra, which I will describe in more detail in a moment. And furthermore, you identify the width metric, what comes on the gravitational side, with the Cartan-Keeling metric of this algebra. And now the important thing here is, and this is where you see already this is really the origin of why you're talking about indefinite Kac-Moody algebras. Because normally Cartan-Keeling metrics on finite dimensional Lie algebras are positive definite, or maybe positive semi-definite, but they never have negative eigenvalues. So you already see that you get something different here. This follows directly from the indefiniteness of the Wheeler-DeWitt Hamiltonian. So that's one thing. And the next thing is, if you now take these wall forms, which I had on, which appear here, so depending on, well, there are certain distinguished walls or leading walls, you take those. And you calculate the scalar products of these wall forms to get a matrix. And this matrix has the dimension of the space of diagonal factors. Okay? And then you find out that this matrix comes out to be the Cartan matrix for a certain indefinite Kac-Moody algebra.
Could you remind me, please, again, what those wall forms were in the previous transparency?
Well, the wall forms were, so you have G-M-N, and then you have the, maybe I should write it down. So we have the W-M, and then we have the beta n. So these are so it's a linear form. This is just the width metric used to contract. And then you have for each wall, you have such a set of vectors. So this is capital A labels these forms.
Are these walls really like a step function or
Yes.
exponentials?
No. In the limit, in the BKL limit, they're sharp. So what it looks like really, so you have this indefinite space of let me maybe draw a light cone, maybe like this. So here, okay. So this is the beta space, which, as I said, has Lorentzian metric, and then you interpose walls here. So maybe even more colors. Let's see. So what this does, it's sort of, there appears a sort of chamber if you insert these wall forms and intersect them. So you have something like this, where each of the walls corresponds to one of these theta function walls, and then this particle bounces around like this. And these are just the BKL reflections in this description. Okay? In this, the dimension of the space is the dimension of the spatial metric. Diagonal, yes. So you will see. A little bit of patience. You look at these Cartan matrices, and you can do this for various models, but let's just restrict to the most interesting case. For four-dimensional Einstein gravity, it's something called AE3. It's a rank 3 hyperbolic Kac-Moody algebra. And the most interesting case is M theory, 11-dimensional supergravity, where this comes out to be E10. I will say more about it. But in any case, this analysis of BKL oscillation now becomes very simple because it turns out that this thing is just what's called the Weil chamber for this Kac-Moody algebra.
What fixes the walls to be the things that are necessary for the Kac-Moody algebra?
Well, this is really the information that sits in here and that you extract out of this Einstein theory coupled to matter. That's explained in our cosmological billiard review. So I cannot explain it in 2 minutes, but there's a certain procedure which is, I think we made an effort to explain it in a pedagogical way, so you can see how this comes.
To be related to Kac-Moody algebra?
Yes, in a certain sense, in the sense that you will see. Anyway, so E10, so it's the thing associated with M theory, but it's also mathematically distinguished. It's what's called the maximally extended, maximal rank Kac-Moody algebra. This is a theorem in Katz's book. If you impose this extra condition of hyperbolicity, then it's the maximal rank. And even more is true. And this is really an amazing property of these indefinite Kac-Moody algebras. Has no analog in finite dimensional algebra theory. E10 contains all hyperbolic, simply laced hyperbolic, simply laced in this case meaning symmetric Cartan matrix. Hyperbolic algebras are some subalgebras.
Hyperbolic means one negative sign in the metric?
No. Let's hyperbolic. So let's be precise. So hyperbolic is indefinite plus the extra requirement regular subalgebras, finite or affine. So affine Kac-Moody algebra is something you know. So it should be such, it's indefinite, but when I take away, reduce the rank by taking away a node, I should not be left with another indefinite. So that's really, this extra requirement says rank is less than or equal to 10. So that's one thing, and second thing is Lorentzian. Because indefinite means you could also have more than one negative direction. So that's a general result. And that you will see that is also not completely without importance. Anyway, so this is a curious result, has no analog in finite dimensional. It would be like saying E8 contains all the simply laced Lie algebras, which is not true. But here it's true.
So this derivation of E10 is in spirit at least independent from Julia's observation.
Well, this goes, of course, now much beyond. Julia's observation was simply counting it's E7 in 4, E8 in 3, E9 in 2, which was then checked. And finally, so this must be E10 in. And the one-dimensional, as I said, has something to do with this BKL limit. That's at least our hypothesis. So what is E10? Well, so here's the Dinkin diagram. You get out of this gravity theory. This extra node comes about because of the 3 form. It's associated with it. The rest is gravity. And it's simply about constructing Lie algebras recursively by what's called generators and relations. The building blocks are SL2 subalgebras, one for each node of the Dinkin diagram, and a set of rules how to glue them together. And then E10 is nothing but the free Lie algebra you get by taking all commutates in all possible ways subject to the Jacobi identity divided by these relations.
So these rules said to be read out from this WMA, those numbers appearing in the wall?
Yes, well that's the scalar products. Sorry. So when you take the leading walls associated with the leading, well, the ones that are next to you, you calculate these products by means of the de Witt metric for 11-dimensional supergravity, and this is what you get. So as I said, it's freely algebra, blah, blah, blah. This is something that works for finite dimensional Lie algebras as well. In that case, the Cartan matrix is positive definite, and then the algebra is finite dimensional. If you make it positive semi-definite, then you get what's called affine Kac-Moody algebras. If you make it indefinite, negative eigenvalues, what's called indefinite. Now this makes just, you would think, well, what's the big deal, adding one node to the Dynkin diagram, but it makes, an astronomical difference, because then you get what's called an algebra of exponential growth. Roughly speaking, it's like the growth of states in string theory, exponential growth. This is also what you get here. And I will not, I can explain it in more detail if you wish. I just want to show you one picture. This was done by Tjeke Nutma, one of our former postdocs. I'm sure you've all seen the octet, meson octet diagram. That's just a root diagram of SU3. This is an infinitesimal slice of the corresponding object for E10. Slice, two-dimensional slice through the E10 root system. You can't even see the point, but each point is associated with one or more Lie algebra elements, independent. And you have infinitely many of those slices.
Sorry, and when you say exponential growth, you mean exponential growth in the number of roots weighted by weights?
Well, I will say this in a moment. You will see. So, so that's one thing. So you have this monstrous growth. The other thing is that if you analyze it by terms of taking away nodes, then you recover many of the duality symmetries that we know from string theory. So here's SL10, there's SODD that you get in certain compactifications. This is 2B, this is n equals 8 supergravity. And you see here the hyperbolicity. This is where it comes in already, because it tells you that it's a monstrously complicated algebra, but if you take away a node, then you have a finite dimensional subalgebra in terms of which it's fairly easy to analyze, at least, so it seems. So here, for example, if you look at this, so here we have the SL9 that you would get from type 2b supergravity. This is type 2a supergravity, and this tells you that if you combine the two, then you will immediately lead to E10. That's, if you think about, combining two asymmetries to b symmetries, what follows here, then you get this monstrously complex thing. So let's be a little more concrete. For this, we take away this node. Then this means decomposing E10 in terms of SL10 subalgebra, and this is what you get. So to be now more precise to your question, what it means is that I take the roots, I decompose them, I attach the number of these roots here. This is what I call level, so the level decomposition. And if I keep this fixed and act just with E10, SL10, then I just get representations of SL10. And then the algebra itself can be decomposed like this into an infinite direct sum associated with these levels. And the exponential growth, or one way to see it, is there's exponential growth in the number of representations as a function of L. This
L being
the number of times this exceptional root appears. So if you do it up to L equals 3, meaning you take this with coefficient 0, 1, 2, 3, then this is what you get. And I'm sure you all know what this is. This is the bosonic fields of 11-dimensional supergravity plus their magnetic duals. If you do the same thing with the 2b supergravity, meaning decomposing it like this with respect to this node or this node, then you will get the bosonic multiplets of 2b supergravity or 2a supergravity. So it always you never use supersymmetry. Supersymmetry is not needed. It just follows from this. So as you know, this has been subject of intense investigation. where, you know, in dualities in string theory, where you use preforms and the dual p-forms. You also talk about something, we call it dual graviton, but sometimes called, what is called Kaluza-Klein monopole. So, you know, people think about, you know, I perform these operations, map one of these things into the other. Now it's all part of E10. And so this is as far as this state of the art goes. But with my student Fischbacher, already in 2003, he was very good with the computer. So we extended this analysis to level 28. And then you already find 4.4 billion SL10 representations, all kinds of Young tableaus. It's, as I said, it's hopelessly, monstrously complicated.
Supposed to be the string spectrum?
Well, if it were so simple. Yes, it has the same kind of exponential growth, but this was another thing I did back in the 90s with one of my students, Gebert. We tried to apply the string vertex operator construction to sort of map this. This you can do, but there appears a problem in the sense that it's not clear how to characterize. I mean, the thing is much more erratic than the string. In string, you have nice partition functions that tell you how many states there are at a given level. There's the DDF construction, all that. This doesn't apply here.
So roughly which one is bigger?
It's not well, I mean, they're both infinite dimensional, so you can embed E10 into something like in a certain Borchardt algebra of rank 10 of physical states of a string, which is bigger, but then the whole problem is how to characterize how E10 sits in there. And this is just as complicated, as we found out, as characterizing the group, the algebra directly.
Sorry, what is the level? Level means what is that?
The level means in the decomposition, when you look at a root, how many times this root appears. So if the 28 means I have 28 times this root times any number of these, and then I already find zillions and zillions of combinations. Okay, so that seems beyond reach. And what's also beyond reach is somehow the Lie algebra structure, because as a physicist, if I say I have a symmetry, I give you the Lie algebra elements or generators, then you will ask, well, what are the structure constants? And then I give you the structure constants, and then you know what the Lie algebra is. Well, here it's known up to, well, L equals 4, maybe L equals 5, but that's it, you know. It seems hopeless to, you know, write down a table of structure constants of 4.4 times 4.4 billion objects. And even if you could do that, you wouldn't have solved the problem, because it's also known, this is the exponential growth, as you continue, it will get ever more complicated. This is different from affine. Affine Kac-Moody is infinite dimensional, but it's a structure that repeats itself. It's the same structure an infinite number of times. So you can write down things very explicitly, but not so here.
So L equals 0, 1, 2, 3, just one represented, you know.
There's just one, yeah. So at the beginning it looks fairly innocuous, but once you go to 5, 6, all of a sudden it becomes more and more and more and more and more and more. I have 300 pages of tables at home in my closet, and I sometimes, in fact, you can find them in this, or some of them. You can just look at it, just to get an impression of what this is, and you get pages and pages and pages of tables, and it's only this thin first slice that we really understand.
So even N equals 4 is not mapped to anything familiar.
Well, you're referring to ADS-CFT dual?
I don't know. See,
Oh, N equals 4 supergravity.
Yes.
Well, you can play this game also for other supergravities, matter coupled or so. You get similar structures, but you know, the fact that it's indefinite, this is always true once you have gravity because of the indefiniteness of the Cartan killing metric. So that's where we are. So I stop here because I want to get to the fermions. So what we have so far is we recover bosonic multiplets dynamics of maximal supergravities by appropriately slicing. So this is really like the M-theory blob, but what we're after, we want to know what's inside. And in such a way that depending on how I slice it, I get to one of the corners. Secondly, E10 knows all about supersymmetry. It seems like we no longer need supersymmetry because E10 has all that information in it. Well, then there's something we can discuss because after all, this has led to the idea that space-time is emergent in the sense that at the Planck scale there is no space-time, but all the information about spatial dependence is somehow contained in this huge Lie algebra. However, so far, even after 50 years, there's no concrete realization of this algebra. We don't know what these 4.4 billion representations correspond to, and what's their physical significance. What we know is if we really combine to A to B to get this symmetry, then we get all this, and we don't know what it means. Then the question is, this idea is very nice with the de-emergence via Lie algebra, but how does it really work, and how do you really get a quantum field theory, space-time, and so on out of it? So it looks to me like this is something that will take, may well take another 50 years to make progress on. So meanwhile, you try to do the things that where you can make some progress. So now I'm talking about how much time do I have left? It's not because.
Yeah, 14 minutes.
Probably 11:30 the class.
So there's a class here at.
Maybe 11:30. So till 11:30.
Okay. So I'll try to be, because this is, as I said, now we're getting to the Fermions. I haven't said anything about the.
Could I ask? So at the beginning you alluded to the statement that some coset of E10
Yes.
would be the set of all metrics and three-form
Yes,
fields.
right.
That has not yet you've not yet shown.
Well, no, but to some extent it has been shown because up to level 3 we can make a precise correspondence between the 11-dimensional field equations with the metric and everything and this group theory. So up to level 3 the information is enough to recover this information about the bosonic theory. But what's not clear is that, I mean, on the field theory side, of course, we want to get the space dependence of these variables. And on the group theory side, algebra side, we want to understand what all these higher representations are. So the question is, what's the correspondence? What's the dictionary, if you think about it in ADS-CFT language, what's the dictionary between the Lie algebra and the space-time dependent degrees of freedom in the supergravity theory?
What is the reason to believe that there is such a dictionary?
Well, first of all, it works perfectly up to including level 3.
But that's just the zero modes, right?
No, well, yes, call them zero modes. But you see, on the one hand, in 11-dimensional supergravity, we're making a spatial spatial gradients, like in BKL. On the other hand, we're making an expansion in these level expansion, and then we're associating the two, and the correspondent works beautifully up to level 3. And beyond that, we don't know how to make it work. So that's our state of the art.
What this, actually, the way you introduced it is from these metric degrees of freedom that live on the diagonal of
Yes.
the wall forms and so on, which was happening in some finite d-dimensional space,
Yes.
which was probably the rank of this. So how is it that this chaotic motion that is happening in that finite dimensional space related to this infinite dimensional structure of which that is?
Well, this is, if you like, this is just a sort of Cartan subalgebra projection of all this. Of course, the actual dynamics will have to take place in the Lie algebra of E10, which is infinite dimensional. So here it's a sort of projection of this onto what happens in the Cartan subalgebra in a certain limit.
So that is some sort of a gauge projection?
Well, I don't want to be too precise on this because it's not clear how it really works. I'm just giving you what we know. So
It has to be the space dependence. This is something.
I mean, the thing is, I can tell you.
How many superspace from point at a point. But now you want to, if you want to make the whole thing You want to take the dynamics of all metrics.
Exactly. So in this PKR language, it would mean that I have all the spatial gradients. Just think about doing a Taylor expansion about a spatial point. And if you look at the Lie algebra, you'll find representations for all these spatial gradients. So that's very suggestive. But it turns out these spatial gradient representations are just an infinitesimal subset of this whole algebra. And we just don't know how all these other things come in. What's their role? Why do you need them? So anyway, let's now get to the fermions, because this is where some recent curious...
I'm sorry, so the spatial gradients, of course, are also infinite dimensional. I mean, there
Yes.
are infinite number of Fourier modes
Yes.
for every...
Yes.
So in what sense is this infinity less than the infinity that you have?
It's just, well, as you know, infinite and infinite, there's something that's infinite and it's handleable in infinity, like in Kac-Moody, and then there's something that cannot be handled, which is even much, much bigger. But it's not, you mean in the sense of cardinality, Aleph and so on?
Level by level. Well, I'm not, so is this really true that the spatial gradient expansion has really something to do with the level expansion?
Yes, well, in the sense that, if I go back to this, that's 28. And there's a spatial gradient, one spatial gradient at each level. So out of these, so you can see how it grows. They have this many representations, and something like 28 out of these are spatial gradients, where I think have some idea what they could correspond to physically. The rest, I don't know.
Where does the coset appear in this?
What?
Where is the coset?
Oh, that comes in. I haven't talked about it, because when you really want to do the equations of motion, you have to go to triangular gauge. You do a level expansion. It's basically what Kremer and Julia did for E7. But of course, it's all based on unknown, like things like the Iwasawa decomposition and so on, that we just use that heuristically to...
Billiards is happening in the coset space.
No, the billiard is just happening in the Cartan subalgebra is part of this coset. Anyway, now fermions. Now fermions, we have learned in supergravity, don't transform under this global symmetry group, but under the maximal compact subgroup. So for 11-dimensional n equals 8, this is SU8. So fermions decompose into 8 gravitinos and 56 spin 1/2. For E8 in 3 dimensions, it's SO16 subgroup, or spin 16 divided by Z2 subgroup of E8, 8. However, here we're talking about representations that cannot be lifted to representations of the global symmetry group. That's important. They're spinorial double value representations. So what is KE10? I know as little about it, or not much more about it, than about E10 itself. But there's a recursive definition, just like Chevalier-Serre presentation, which goes as follows. And the easy way to think about it is, if you know how, if you take SLN, you know how to define the maximal compact subgroup, SON. In terms of an involution, you say involution maps matrix to minus transpose of the matrix. And then the fixed points are the antisymmetric matrices, and this is what makes SO10. So okay, so you simply repeat this prescription for the generating objects, and then you take the invariant generators, which here like this. So this is really like, if you think about SL2, then this is just this matrix. Okay, so that's easy. So you simply take these combinations, one for each node of the Dynkin diagram, and you can again write generators and relations. This is a bit different from Chevalier-Serre. This is not like the usual Kac-Moody algebra. And for KE10, for example, you get this set of rules. So this looks fairly simple. And this generates an algebra, of course, subalgebra. But this algebra for E10 is no longer a Kac-Moody algebra, because what you lose is the triangular decomposition, which is crucial for Kac-Moody. So this is a new kind of algebra, And we now have to look for representations of we can construct.
So if you think of SON as a maximally compact subgroup of SLN, then okay, then it would be half dimensional. Like
Yes.
But if you think of SON as maximally compact subgroup of SON comma 1, let's say.
There as well you can, yes.
Involution.
There's always such an involution. I mean, there's the topological definition, of course, in the sense of compact, but that doesn't work for infinite dimensional, as you know. The unit ball in the Hilbert space is not compact, unlike it would be in the finite dimensional space. Well, they also had the issue of infinite dimensional topologies, blah, blah, blah. So that's, you can get infinitely distracted if you start thinking about this. So anyway, these are the generating relations. And now can you ask yourself, what do I get? Well, if I do it for the finite dimensional ones, of course I recover the finite dimensional asymmetry groups of supergravity. Of course, here it's infinite dimensional. This was there's someone by the name of Hermann, not to be confused with the Hermann from Queen Mary College. It's a mathematician who has proved that, or shown that this defines really an algebra. But about these things, not much is known. And first, except, well, this is something that we came up with because we just looked at the 11-dimensional supergravity and asked ourselves, if we take the fermions of 11-dimensional supergravity, the gravitino, how does this thing act on it? And then you discover that the 11-dimensional gravitino is a finite dimensional representation of this infinite dimensional group. This is a very strange thing because you would think, well, it has to be infinite dimensional, but no. They're finite dimensional representations, which means that this thing is not simple because it has non-trivial ideals. This means that the fermions of 11-dimensional supergravity, the gravitino in a certain gauge, which is like the Coulomb gauge, transforms as a representation of this E10 in the sense that we can find a concrete realization of the action of these x's on the gravitinos that satisfy the relations which I showed before. So this means also that the fermions of n equals 8 supergravity, the 8 and 56, spin 1/2, and 8 gravitinos, also transform under this. So let's now, I'm now jumping because I said I wanted to find some relation to real physics of this. And so here it is. And this is something that goes back to an observation by Murray Gell-Mann, which he made back in 1983. Because in those days, they were somehow trying to match the fermions of n equals 8 supergravity to standard model fermions. And he first tried this in 78. It didn't work. Why didn't it work? Because he said there's an SO8 gauge group that contains at least this. It's non-chiral, therefore let's forget about SU2 weak. Let's just think about SU3 color and U1 electromagnetism, symmetries that are supposed to survive to the lowest energies. Let's take the spin 1/2 fermions, decompose and see whether it fits. And now this is what you get. Octets, sextets, triplets. And then Gell-Mann said, okay, that doesn't work. This he already knew in 78 before the construction of the theory, so that didn't work. And then came Crémer-Juliard. There were attempts to exploit the SU8R symmetry and so on, which also didn't work. And in 1983, he made this funny, really strange suggestion. He said the SU3 here should not be identified with SU3 color, but the diagonal subgroup of an SU3 color and a putative SU3 family that relates the 3 generations. And then he put these things, so here up a charm top, and you put them in some representation of family, in this case 3 bar, and so on. You take the diagonal subgroup, and then you get something that precisely fits with what you get from n equals 8 supergravity. What about the electric charges? In n equals 8 supergravity with this decomposition, this is what you get. Again, didn't seem to work, or that doesn't work as it stands. But then he observed that if he allows himself to throw in a spurion shift of plus or minus 1/6, then he can make it work. So you see that this scheme, as far as it goes, does precisely agree with the standard model fermions. And if you allow yourself this trick here, by adding, subtracting 1/6, you get precisely the electric charges of the quarks and leptons. Okay, so it's strange, right? I've been obsessed with this, you know. But for many years, I tell people, isn't it strange, you know? If it's wrong, you wouldn't expect it to fail by so little. And but in those days, you know, people said, well, you know, we have this MSSM, we switch on LHC, we'll see a plethora of supersymmetric particles, new spin 1/2 degrees of freedom, and then of course we're dead with this. You can forget about it. Well, this is why I showed the table in the beginning. As you know, nothing. It could well be that this is it. We've seen it all in terms of spin 1/2 fermions.
Electric charge is the charge under that U1?
Well, it's not this U1, you will see in a moment, because this U1 would give you these charges.
Right, I meant the
which
fake
are
electric charges.
the left. So these are the n=8 electric charges that you would get, and they don't fit. And then he said, but if I do these, allow myself this dirty trick, then it does work.
Yes.
So,
You do it by hand, this Q plus minus Q?
yeah, it's of course entirely by. I mean, all of what I'm going to tell you now, it's kinematics. It's sort of, you know, like doing strong interactions in 1960. There was no dynamics, just group theory trying to. So one thing that we did with Nick Warner back in 1985, we showed that this scheme is actually dynamically realized in the sense there's a stationary point of n=8 supergravity that realizes this. But we put it aside for many years, waiting for the LHC results. And now that we know a good chance that this is it, we decided, well, is there a way to fix this? And here we go. Yes, there is. There's a way to deform the U1 to match these, to make this work. So it means that the U1 that you get from n=8 supergravity is not quite the right one. You have to deform it a little. And here, this is work I did with Krzysztof Meissner 4 years ago. We pointed out that this can be achieved by looking at doing this funny transformation. And it's funny because you can see it's not in SO8 or SU8 because this would be the action on the three-form representation if it was just SU8 or SO8. But you have to add this extra thing which is not in SU8. So this means that in order to fix this, we have to go outside supergravity. There's no way to make it work. So it's not. So here, these details I don't want to go into. But what I want to argue now or show you that it's not in SU8, but it is in KE10. Now I have a more technical slide here, but this let's not look at the details because there's no time. Yeah.
This matching that you flashed in the previous slide, are there degeneracies or? I mean,
Are there what?
Degeneracies. I mean, because the supergravity may have more fermions.
No. Sorry. This is one thing that I forgot to mention. It's 8 gravitinos, 56 fermions, but you have to remove 8 spin 1/2 for Brout-Englert Higgs mechanism to make the gravitinos massive. This Gell-Mann said, okay, after this I end up with 48, which is just the right number, including right-handed neutrinos. They're here in terms of left-handed antineutrinos. So they're all here. So now I'm saying that I can fix up the charges, but I have to go beyond SU8, and in fact I have to go to K of E10 in order to do this. I will not go through this in detail because you have to concretely show with this realization of KE10 on the finite dimensional fermion representation that there is some transformation that actually realizes this funny generator here. And this you do because we have a realization, concrete realization on these fermions of KE10 and one transformation associated, well, again, I would need more time to explain this, But anyway, there are infinitely many what's called real roots that square to 2. And we have an action here that I can explain if you wish in more detail later. But anyway, there's a concrete realization of this. So we can simply, by making a search through this space of transformations, check that there's one, in fact, infinitely many, that realizes this. So this is, as I said, I cannot explain it in detail, not in 5 minutes. But anyway, what comes out of this is, in order to match this, or to rectify this Gell-Mann prescription to make it match with the standard model, we have to go infinite dimensional. You need the full power, all the roots of E10. You cannot do it with the finite dimensional E8. You cannot do it with the affine E8, the E9. You have to go all the way. And in fact, in more recent work with Krzysztof Meissner, this appeared last year in PR. We even got it into PRL, amazingly. We even have been able to undo this thing and actually find a realization of the full standard model group on these. And this is realized within KE10. And furthermore, there is a family symmetry, SU3 family, which I argued before. But the strange feature here is this doesn't commute with the electroweak SU2 because, as you can see, the up and down, which would make up an electroweak doublet, they're put in different representations of SU3 family. So this is something we try to do without, but this Gell-Mann scheme only works if you do it in this way. So this is what we've now done. The open question, of course, how we're still at one spatial point. How does this unfold to give space-time dependence and gauge symmetries and so on? We have certain ideas how this could go. But finally, I have 3 more transparencies. Let's have a look at the gravitinos, the massive gravitinos, because this is something Gell-Mann didn't talk about. He didn't know how to implement his funny shift. Now we know with KE10, we know what to do. And you have H gravitinos, massive, they decompose like this. And you see they have very unusual features. They're not just one like in MSSM, they're 8. And 6 of them transform under interact strongly. So I guess at this point, any MSSM model builder will probably freak out because the dogma is that the gravitino is Majorana, doesn't couple it to anything, we don't see it. Maybe it's dark matter. Here it's different. And now we will hypothesize that this is actually what makes up dark matter. And if these are super heavy particles, one of the things you have to worry about that these heavy things don't decay right after the Big Bang. Certainly if they have usual standard model interactions, you would expect them to decay. But now look what happens. The quantum number assignments here are such that they just cannot decay. Because there's nothing with this, charge content. There are no charged final states in the standard model that would have these assignments. You see this, if the up quark has this, but it has 2/3. This has 1/3. The down quark does have 1/3, but sorry. Anyway, it's just inverted, so the 3 bar would be, so down quark has -1/3, sorry, but it's a triplet, not an anti-triplet. You see, no matter how you do it, it just does, even if you wanted to decay, it cannot because the quantum numbers forbid this.
Single particles, because they can come in groups.
Yeah, well, I have no idea how they would interact, but the idea would be, of course, they have to respect these symmetries because that's believed to survive to the lowest energies. So they should certainly respect charge conservation. So that would guarantee stability.
Sorry, are you saying no collections of these can decay into collections of standard model particles also?
Yeah, there's no final state in. I mean, if you take any of that, there will be very rare. The only way to make them disappear is via mutual annihilation. I will get to this. But if they make up dark matter, they have to be extremely dilute, because otherwise we would see them. So here is this, if you like, crazy proposal. It is crazy. but no more crazy than other ideas that have been put forward, we think. So they have this charge that make them stable. And now what should be the abundance be? Because we know what the dark matter density in our neighborhood of the galaxy is. It should be like corresponding to 1 proton per cubic centimeter. That's about if proton were the dark matter particle. But if you scale this up by a factor of 10 to the 18, it seems like you need only one of these particles in a cube of 10,000 cubic kilometers, and which means that, even if they're there, they will be hard to see. We've checked that, the WIMP searches they've done, they have like fiducial volumes of a few cubic meters. You can sit there, of course you can wait for 200 years, and maybe one of these things comes through. And but another idea that has popped up here is a new kind of search, maybe in terms of what we call paleodetectors. It's like looking for fossils in old rocks, namely traces, because this thing will, because it's so heavy, it will just go through the earth like, like a cannonball will fly through a swarm of mosquitoes. It will just go through, but it will leave a distinct trace because it has this usual interaction. So that's a I'm not sure whether, there's some people who have talked about this, but I'm not sure to what extent we have the technology to do this. So this is the final thing, because we now also have strongly interaction gravitinos, and the only way for them to go waste via mutual annihilation. And here the idea is that, well, as dark matter, they're so far from each other that it's very unlikely that they will ever annihilate. But the hypothesis, if dark matter gets collected or accumulated inside stars, which is something that cannot be ruled out, and then this star collapses to a neutron star, that in this limit, the gravitinos get sufficiently close to each other that they can annihilate in appreciable ways. And you see what happens if this is really true. If you have an annihilation of a Planck mass particle, so you have like 10 to the 19 GeV, that will be released upon annihilation. Okay, but that's not what you get, because at CERN we see that when you collide protons, you don't just get single particles, you get showers. And for the new accelerator, FCC, they're talking about each collision will give rise to 1,000 hadrons. And we take that formula, we widely extrapolate it to the Planck scale, and then you see you get about, for each collision, about 1 million particles, hadrons. And this will give rise, so each particle will have like 10 to the 13 GeV, which is like 10 to the 22 electron volts, which is not far from, here you shouldn't pay too much attention to factors of 10 because there are too many uncertainties. But anyway, this is approximately the energy they've seen in these observations of cosmic high energy events in this Argentinian observatory. So this could be explained by this, because, and the other thing that could be explained here is that what they see is heavy ions, not just protons. And the idea is that these things happen in the crust of the neutron star. The crust of the neutron star has ions in it, and not just neutrons. That in these processes you will sort of kick out also these ions, and these are the things they see. Here, as I said, we would also try to estimate the rate. The paper was rejected because the referee said, but you've doctored these numbers so as to get what you want. It's a real roller coaster, because you're multiplying 10 to the minus 50 times 10 to the 30 times, it goes up and down, up and down. And you have to make various assumptions in certain places. And the referee is correct. We have doctored these values just to see whether it's possible at all. So this is not a definite prediction. But if you do this, then you get rates that are very close to the ones you observe, which is like 1 per month in this 3,000 square kilometer array. So my hope, not claim, because this is still too crazy, would have to be confirmed by other facts, but it could just be that these ultra-high energy cosmic ray events originate from the annihilation of the massive gravitinos that we get from this theory. So it would be like hints of K10 or E10 in the sky. So I'm now finished. Well, this was a little bit of a tour de force, trying to tell you that E10, K10 unify the known duality symmetries. It's very important that this be realized in terms of emergent space-time. There's no way to get this within quantum field theory. All of this would have to be emergent. How, we don't know. So this remains an outstanding challenge. And I've exposed some links. In particular, what I'm intrigued by is the fact that possibly, in order to match what we see in nature with this ansatz, you must go infinite dimensional. There's no way to work with just a finite dimensional duality symmetries that people have worked with. And of course, this is my personal hope that we'll not just end up with 10 to the 270,000 possibilities, but that there's actually a reason why the standard model looks the way it looks, and especially with 3 families of quarks and leptons. Okay, thank you. Yeah.
So one thing we said is that if it does form dark matter, then it would probably be hard to observe
Yes.
because of low perception.
Yeah, well, also low densities, low abundance.
Or low density.
Because the formula is cross-section times density times velocity, average velocity. So that gives you, that's what gives you the rate.
So did I understand right that your candidates for dark matter were color non-neutral?
Yes. But, well, they could of course form bound states with quarks and leptons. But then you see that the color singlet states that you get, they're always fractionally charged. And there's no fractionally charged color singlet state in the standard model, which shows that these things have no way to decay.
So the physical objects would be color singlets because of confinement.
Yes.
That would be fractionally charged.
Yes, exactly.
And that doesn't contradict some Dirac something or the other. Or it would tell you that monopoles.
Well, maybe it does, but I just haven't thought about it. But you know, I admit it's totally crazy because it goes completely against what people have this idea that it is weakly interacting. Even when they're talking about WIMPs or WIMPzillas, even 10 to the 15 GeV, they always assume that they weakly interact. So this flies directly in the face of this assumption that's made most of the time.
I thought you were talking about some color flavor locking.
This is simply a description, a verbal description of what Gell-Mann did. This is flavor color lock, family color locking. Interestingly, there's some work by Wilczek of around 2000, where he has a new description of QCD, and where he says the real symmetry is the diagonal symmetry, subsymmetry of color, and in his case, flavor. So he calls it flavor color locking, which is also kind of weird. In spirit, it's very similar, and he shows that you can get all the results of QCD from that scheme. So it really, it's completely, you know, in school we learn that hadrons or baryons are made of 3 quarks, but in his scheme, no, it's not like this, but because he assumes that ultimate symmetry is really the diagonal subgroup, but then he shows that all the predictions of QCD come out to be the same.
That's in some region of high potential.
That's indeed his work. He was concerned with high density, high temperature phase of QCD. But then in his paper, then most people say, as you go down, there's a phase transition. He says very explicitly, I have evidence, this is evidence that there is no phase transition. So this is it. Even if you go away. So he wrote quite a few papers on this with his collaborators, but by now I think there's not much more on this. Probably because, he did the things that could be done, but it's an idea that sort of points in a similar direction as this.
I seem to remember graphs in which the CFL phase, the color flavor locked phase, is it's very far away from the origin.
Yes.
In the T mu plane.
That's true.
So it's some it's some exotic thing that's happening over there, and
yeah, but as I said in this paper, you find the explicit statements. He thinks, because by analyzing this, he thinks there is no phase transition.
I see.
Any more questions?
Well, we have to leave, I guess.
If